Okay, so let us continue with our review. So in the context of arithmetic and geometric series, it is natural to talk about linear versus exponential growth. So the math fact is that exponential growth is much faster than linear growth. So here is exponential growth with the base c to be bigger than 1. So here it's 2 to the power of n, and here it's linear growth, scaling linearly in n, and as you can see, for n like 16, the exponential growth is by far larger than the linear growth. Okay. So this brings us to the notion of the family of exponential functions. So 2 to the n, 2 multiplied with itself n times, is an example of an exponential function with variable n. In general, for any fixed real number a, let's say a equal to 10, which is the case of the decimal base, a to the power of n is also an example. In calculus, we learned the definition of a to the x, which where x is a real number, for instance, x equal to 0.5 or x equal to pi. In mathematics, exponential function can also mean fxy equal to x to the y, or often means gx equal to e to the x, where e is the Euler constant 2.71828. Okay? So these are various things to the power of x. Properties of exponential functions. So a to the x times a to the y is a to the x plus y, and a to the x to the y is a to the x times y, and the derivative of e to the x is still e to the x. So exponential functions a to the x with a bigger than 1 are strictly increasing, so it has an inverse function which is the logarithm. So if you have a strictly increasing function, then you can have, of course, the inverse function. So in the case of the exponential function with the base a bigger than 1, the inverse function is a logarithmic function. So for example, if 10 to the x equal to y, then x equal to log y base 10, and for example, one example of this is as follows. So remember that the basic equation is 10 to the x equal to y means x equal to log y base 10. Similarly, 2 to the 5 equal to 32 is equivalent to saying that log 32 base 2 is 5. The inverse of e to the x is called the natural logarithm and is denoted by ln x, which is log base e of the number x. So just in analogy to the properties of the exponents, you have basic properties of logarithmic functions. So log x times y is log x plus log y. Log x to the power of y is y log x. The derivative of log x is 1 over x, and so on. So here is a simple math fact about approximation. Log 1 plus x is approximately equal to x. So x is something quite small. So x 0.5, 0.2, 0.1, 0.05, and so on. So log 1 plus x is approximately equal to x. And using calculus, when the size of x, the norm of the mod of x is absolute value of x is smaller than 1, then log 1 plus x is x minus x squared by 2 plus x squared by 3 minus x squared x to the 4 over 4, and so on. Okay? Any questions? So this is the basic expansion of the logarithm of 1 plus x, and the point is that for x very small, the higher order terms are super tiny, so essentially log 1 plus x is approximately equal to x. Okay. Multiplication principle. Assume that a task can be broken up in two consecutive so this was so much about the geometric series, arithmetic series, exponential growth, linear growth, and then the logarithmic approximation log 1 plus x is approximately equal to x. This is followed by a recap of combinatorics or permutations and combinations. So we start with the multiplication principle. Assume that a task can be broken up into two consecutive steps. If step 1 can be performed in n1 ways, and for each of these n1 ways, step 2 can be performed in n2 ways, then the task itself can be performed in n1 times n2 ways, right? So it's like the following. So I can so there are, so suppose I am going to a destination, and between the final destination and myself, there is a intermediate stop. So there are a number of ways in which I can reach this intermediate stop, and then from the intermediate stop, then there are a number of ways in which I can reach the final destination. So suppose there are n1 ways of reaching the intermediate stop and n2 ways of reaching the final destination from here, from the intermediate stop, then the total number of ways of reaching the final destination from where I start is n1 ways of reaching the intermediate stop times, for each of the n1 ways, n2 ways of reaching the final destination, which is n1 times n2 ways. Okay. And this is codified in the general multiplication principle. So if a task involves a sequence of m steps, where the ith step can be completed in ni ways, then there are n1 times n2 times da 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 up to nm ways to complete the task. So the necessary condition for this is that the ways each step can be completed are independent of each other. Okay? So for each way of performing the first step, you should have n2 ways of performing the second step, and so on. So these numbers ni are essentially independent of each other. So here is an example of arrangement in a row. So let P and K be the number of ways of arranging in a row k different objects taken from n different objects. Then P and K is n factorial over n minus k factorial. So here the order matters. So P and K is the k permutations of n denoted by, so these are the various notations. So if you have n objects and you want to arrange them in a row, if you want to take k objects from them and arrange these k objects in a row, then the total number of ways is n factorial over n minus k factorial. Okay? So arrangements in a row. So there are, suppose there are 3 red beds, 4 green beads, and 5 blue beads. So if you so the total number of ways to permute the 3 red beads among themselves is 3 factorial. Total number of ways to permute the 4 green beads among themselves is 4 factorial. Total number of ways to permute the blue beads is 5 factorial. So the number of ways to arrange 3 red, 4 green, and 5 blue beads in a row is, total number of beads is 3 plus 4 plus 5, which is 12. So total number of beads factorial divided by the mutual permutations, the number of mutual permutations of each kind of beads multiplied with each other. So 12 factorial over 3 factorial times 4 factorial times 5 factorial. And this is the more general version of this is that the number of ways of arranging in a row n1 identical objects of type 1, n2 identical objects of type 2, and nk identical objects of type k is equal to n1 plus n2 plus nk factorial divided by n1 factorial times n2 factorial times nk factorial. So this is, so the example with the beads is just a particular instance or a particular example of this theorem. Okay? Any questions? Circular arrangements. So in how many ways can you arrange n different objects in a circle? So if they were on a line, there would be n factorial many ways. But remember that you are on a circle, so the circular order doesn't matter. So in principle, you could just shift the objects in a clockwise direction one by one, and you will essentially get the same circular arrangement, and you have n number of such shifts. So the total number of ways you can arrange n different objects in a circle is n factorial divided by n, which is n minus 1 factorial. Okay? Combinations. So this was about permutations and circular permutations. Now we come to combinations. So let C and K denote the number of ways of choosing K objects from a set of n different objects. Then C and K, the number of ways of choosing K different objects from n different objects is n factorial over k factorial times n minus k factorial. Remember a few slides ago we have seen an example where you where you arrange in a row k different objects from n. So this is about that was about order. So here you do not really care to arrange them in order. You are just content with choosing collect bunch of k objects from the original n, and that is n factorial over k factorial times n minus k factorial. Binomial theorem. So the numbers n choose k are also called binomial coefficients since they appear in the binomial expansion of a plus b to the n. So in general you have the binomial theorem, which is a plus b to the n is some k running between 0 and n choose k times a to the n minus k times b to the k. Okay. So and these coefficients are known as binomial coefficients. So this was about this slide. The last few slides were about arrangements and counting and permutations and combinations, and we culminated with the binomial theorem. So any questions about arrangements and permutations and combinations and binomial theorem? Okay. So if there are no questions, then let's move on to probability. So in probability, we start with random experiments. So what is a random experiment? An experiment is a situation whose result or outcome depends on chance. For example, tossing a coin, there are 2 possible outcomes, head or tail. Throwing a dice, there are 6 possible outcomes. Picking a card from a deck, there are 52 possible outcomes. Tossing a coin twice, now there are 4 possible outcomes, because you can get, if you have two coins, you can get head for both, head, tail, tail, head, and tail, tail. So 4 possible outcomes. So random experiment is a situation, or an experiment is a situation where the outcome depends on chance, and probability is essentially the science and the math of studying random experiments. So sample spaces, the set of all possible outcomes of an experiment is called sample space associated with the experiment. So now that you have random experiments, the outcome of the random experiment are you are interested in the outcomes of this random experiment, because you are going to build your probability model on the basis of these outcomes. So these outcomes of the random experiment, if you collect them together, this is called the sample space, which is the totality of all the outcomes of a random experiment. An element of the sample space is an outcome of the experiment. For example, if you toss a coin, then the sample space is h comma t, where h is head and t is tail. Throwing a die, s equal to 1, 2, 3, 4, 5, 6. So the outcome can be anything, any integer between 1 and 6. So that's the sample space for throwing a die. Picking a card from a deck, so you can you have the suit, which is the figure diagram in front, and you have the number from that suit. So this is the combination of the suit and the number is your sample space. Tossing a coin twice, well, head, 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 tail, tail, head, and tail, tail. So that's an example that we saw just now. So these are examples of sample spaces. So after sample spaces, you need to consider events, which are essentially, so in probability you talk about chances. So the chance, you have to associate the chance to something. So the object that you associate the chance with is an event. In other words, you talk about the chance of an event occurring. So what is the event associated with an experiment? So in an experiment of throwing a coin twice, it's HH, HT, TH, and TT. Getting the same result twice, so you can look at the event which is getting the same result twice, which is a subset, head, head, and tail, tail. So this is so an event, heuristically speaking, is a phenomenon with which you associate chance. Mathematically speaking, if the sample space, if you think of it as the totality of all possible outcomes or a set, then an event is just a subset of the sample space, so it's a sub-collection of the outcomes of the experiment. So in the experiment of throwing a dice twice, the sample size of the sample space is 36. The event getting the same number is given by 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So this is the event of that you get the same number on your die if you throw it twice. Okay. So of course, the sample space is any combination of two integers between 1 and 6. The event that you get the same number twice is essentially repeated 1, 1, or 2, 2, or 3, 3, da da da, up to 6, 6. So equally likely, if each outcome of a random experiment has as much chance of occurring as any other, then we call them equally likely. This is a kind of fairness. There is no preference for any particular kind of outcome over the others. So equally likely is a very important concept in probability. So it tells you that there is equal chance of the various outcomes happening. So for example, if you toss a fair coin, a head or tail is equally likely. So the probability of head is equal to probability of tail is 1/2. Tossing a fair dice, each of the 6 faces are equally likely. So the probability of getting any number on the die is 1/6. Let A be an event in the sample space S, that is A is a subset of S. The probability of the event A is cardinality of A divided by the cardinality of S. Thus, this is the so the event A is a subset. You look at it as a subset of the sample space. So probability of A is just the size of the subset A divided by the size of the sample space. So it's the size of the total number of outcomes which favor the event A divided by the total number of all possible outcomes. Okay, so that's the probability of event A. Of course, we heuristically know, or we heuristically can feel or understand what do we mean by chance of an event, but this is an exact mathematical description of this concept. So thus we see that computing the probability of an event basically involves counting, and we only consider finite sample spaces in this course. So why does computing the probability of an event basically involve counting? Well, you have to count the size of the set A. In other words, you have to count the total number of outcomes that favor A. Similarly, you have to count the size of the sample space S, or you have to count the total number of outcomes which favor the total number of possible outcomes in the sample space. So tossing a coin 3 times is an example. If you toss a coin 3 times, if you are looking at the event that you get the same outcome 3 times, so head, 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 tail, tail, tail. So then probability of A is 2/8, which is a quarter. Okay. So again, you are just counting the total number of outcomes which favor the event A and dividing by the total number of all possible outcomes in the sample space. So probabilistic formulation of principles. So the addition principle is that if A and B are disjoint subsets of S, then we say that A and B are mutually exclusive events. Then probability A union B is probability A plus probability B. That is, you have this equation. So this is the case when the two events A and B are disjoint. So A and B never occur together. So for example, if a day is either sunny or rainy, so a day may be sunny, rainy, or cloudy, and you are looking at the probability of the event that the day is either sunny or rainy. Okay, so definitely sunny and rainy cannot occur together. So these are disjoint events. So these are examples of disjoint events. So another principle is the principle of exclusion and inclusion, or principle of inclusion and exclusion, or PIE. If A and B are events, then probability A union B is probability A plus probability B minus probability A intersection B. We also see that A complement is the complement of A in S. So this is the if A is the event, then A complement is the event A not occurring, or the non-occurrence of the event A. So, and the probability of A complement is just 1 minus the probability of A. Any questions? Okay. So, so these are some basic principles of probability, and once we understand that, we come to the important notion of independent events. So, suppose you toss a fair coin twice, would you expect the outcome of the first toss to influence the outcome of the second toss? This leads to a very general and important concept of independence of events. So, basically, if you toss a fair coin twice and your two tosses are not connected with each other, then the tosses, in a natural sense, they will be independent of each other. And there is in probability, there is a concrete mathematical way of expressing this idea of independence in terms of a mathematical equation, and that is the following: if A and B are two events, then A and B are independent events if probability A intersection B is probability A times probability B. Okay? Mutually independent events, we say that the events A, B and C are independent events if so they are mutually independent if all these equations hold. Okay? Probability A intersection B is probability A times probability B, A intersection C is A times C, B intersection C is B times C, and A intersection B intersection C is A times B, probability of A times B times C. Okay? And the events that are not independent are said to be dependent. So, this is about independent events. So, next we come to binomial distributions, which is which actually involves independent events in a very interesting example, but at the moment we will take a 10-minute break and we will continue after the break. So, let us continue with our lecture. So, we consider the binomial distribution. So, if a coin is tossed n times, then so suppose you have a coin that is being tossed n times, and the probability of a head in each toss is p. Assuming that the tosses are independent of one another, the probability that there will be exactly k heads is equal to probability x equal to k, which is n choose k times p to the k times 1 minus p to the n minus k. Here the sample space S has a size 2 to the n. There are c and k elements in S with exactly k heads. So, let us try to analyze this. So, if you look at the event that there are k heads, so these k heads, if you think of the n heads, n tosses in a row, so you can think of them as a long string of h's and t's, and exactly k heads means exactly a string of n h's and t's with exactly k h's. So, the number of such strings is exactly going to be the number of ways of choosing the positions for the k h's out of the n tosses. So, number of ways of choosing the positions for the k h's out of the n positions is n choose k, and and each toss is independent of each other. So, for the k h's you get p to the k, p multiplied with itself k times because of k independent heads, and 1 minus p to the n minus k. So, 1 minus p for each tail and n minus k tails. So, n minus k 1 minus p's multiplied with each other. Okay. So, here the sample space has size 2 to the n. There are c and k or n choose k elements with exactly k heads. The probability of obtaining each specific sequence of k h's and n minus k t's is p to the k times 1 minus p to the n minus k because of independence. So, this explains why the probability of getting exactly k heads is n choose k times p to the k times 1 minus p to the n minus k. Okay. So, now let us tackle the notion of conditional probability. So, if A and B are events in a given sample space S, the conditional probability of A given that B has occurred is denoted by probability A given B, which is probability A given B is probability A intersection B divided by probability B. In fact, it is just shrinking the sample space to B. So, basically, if you are revealed some information about the outcome of the experiment, then based on that information, you can update your chances of the various properties of the outcome, right? So, this kind of update is essentially the notion, essentially captured by the notion of conditional probability. And in fact, it is just shrinking the sample space to B, because essentially telling you that the event B has occurred is essentially telling you that the outcome is a member of the set B. So, now you should scale everything restricted to the set B, because you know that the outcome is already one of the members of that set. So, here is an example. Here are some examples of properties of independence. So, if A and B are independent, then probability A equal to probability A given B equal to probability A given B complement. Probability B is equal to probability B given A is equal to probability B given A complement. Okay. Any questions about conditional probability? So, random variables. Sometimes we are interested in functions from the sample space S to real numbers. We refer to those functions as random variables. So, for example, when we toss a coin n times, the sample space has 2 to the n elements. Each of them is a string of length n consisting of heads, h's and t's. The function x mapping S to R is defined by counting the number of heads that appear. So, if you look at the random experiment of tossing a coin n times, then the sample space has 2 to the n elements, which are all possible strings of length n involving h's and t's. Okay. Now, we already looked at the quantity which counts the total number of heads in such a string. So, this is so if you look at it, it is, if you think about it, the total number of heads is just a function where you input the string of h's and t's that you receive from the experiment, and the output is just the total number of heads. So so since the outputs, since the outcome of the random experiment, that the specific string you are working with, the string of h's and t's of length n, since the specific string you are working with is of length n, and is a random string because the experiment is random, therefore, the function which sort of counts the total number of h's in the string is also, its output is also random, right. So, this function is a random function and it is called a random variable. So, these are functions of the so these are examples of random variables which are essentially functions which take in as input the outcome of a random experiment, and the output is a number. And because the input, that is the outcome of the random experiment, is random, the output of this function is also going to be random, and therefore, it is called random variable. So, probability and random variables. So, since the value of a random variable is determined by the outcome of the experiment, we may look at probabilities to of the possible values of the random variables. So, we discussed just now that the output of a random variable, which is a function of the outcome of a random experiment, is going to be random because the random experiment itself gives us a random output. So, therefore, we can just forget about the big random experiment behind running behind the scene, and look at the random variable and its value. So, the output of so we can just look at the value of the random variable. Since the value of the random variable is random, we can associate to each value the probability of the random variable taking that value. So, we can think of the probability that the random variable equals A, which is the probability of the set of all the outcomes which lead to x of s being A. Okay. So, so this is S of A, which is all the outcomes for which x of s is A, is a subset of S, and therefore, it is an event, and in fact, it is the event that x equal to A. So, just as a case in point, if x is the if x is counting the total number of heads in the random experiment, then S sub A is the event that in a string, in a sequence of n tosses of the coin, there are exactly A heads. Okay? So, this is an example. Expectation. If x is a random variable, then the expected value of the expectation of x, denoted by Ex, is defined by summation x times probability x equal to little x. So, this is summation ai times probability x equal to ai. So, expectation x is just the weighted average of the possible values that the random variable can take, and the weights being the probability that x assumes that value. Okay? So, expectation of x is just the weighted average of the values of a random variable, and the weights being the probabilities that x assumes that value. So, an important property of expectation is linearity. So, if x is a sum of random variables x1, x2, xk, then expectation of x is just the sum of the expectations of x1, expectation of x2 up to expectation of xk. And notice that we do not need to assume anything about the interrelationship between the various random variables xi here. So, they could be independent, they could be dependent, we do not care. So, Benford's law, a set of numbers is said to satisfy Benford's law if the leading digit. So, suppose you have a set of huge table of big numbers. So, you can look at the leading digit d between 1 and 9, and this and you can look at if you have a large number of such entries, you can look at the if you have a very big table of such numbers, you can look at the frequency of the various digits being the leading digit, and suppose the leading digit satisfies the frequency distribution, P of d is equal to log base 10 d plus 1 minus log base 10 d, which can be simplified as log base 10 of 1 plus 1 over d. So this is exactly the the situation where you have a large table of numbers and you are looking at the leading digit. So the leading digit is something between 1 and 9, and you are calculating the frequencies of the leading digit, and the frequency of the leading digit d is log base 10 1 plus 1 over d. Okay. So if this condition is satisfied, then the set of numbers is said to follow the Benford's law. Indicator variables and their applications. So indicator variables are extremely useful type of random variables for solving problems. For any event A, we denote by indicator of A the random variable that takes the value 1 if the event A occurs, and takes the value 0 if the event A doesn't occur. So for example, in coin tossing, A can be the event that there is a head. So indicator of A takes the value 1 if the coin falls head, and takes the value 0 if the coin falls tail. So A is an event, and for every event A you can define the indicator of A. So what is this random variable? Well, you run the random experiment, look at its outcome and check if the event A has occurred or not. If the event A has occurred, then indicator of A is 1. If the event A did not occur, then the indicator of A is 0. And it's easy to see that the expectation of indicator of A is just the probability of A. Okay, so that's a useful property. So here is the simple immediate application of indicator random variables. So calculate the expected number of heads in n tosses of a fair coin. So let Ai be the event that ith coin falls head. Then the total number of heads in n tosses is indicator A1 plus indicator A2 plus up to indicator An. So let's try to parse this a bit. So Ai is the event that the ith coin shows head. So indicator Ai is 1 if the ith coin is head, 0 if it is tail. So what is the sum of all the indicators, indicator A1, indicator A2 up to indicator An? Well, if you sum all these indicators, you are just summing a bunch of ones exactly for those eyes for which a head has fallen. In other words, you just count 1 for every occurrence of head. Okay? So the sum of these indicators A1, A2 up to An is exactly the total number of heads. So the expected number of heads is the expectation of the sum of these indicators, which is by linearity of expectation, which we saw a couple of slides ago. The expectation of the sum is the sum of the expectations. So expectation of the sum is the sum of the expectations. So let us write an intermediate step. So expectation of the sum is just the sum of the expectations of the indicators. Expectation of the sum of the indicators is just the sum of the expectation of the indicators. But expectation of the indicator, as we saw in the last slide, is just the probability of that event. So expectation of indicator of Ai is just the probability of Ai, and if you sum the probability of Ai, it is half n. Okay, because probability of Ai is a fair coin, so probability of Ai is 1/2 for each eye, and if you sum 1/2 n times, you get half n. Notice that we did not need to use any independence between the coins. Okay. Expectation, and so any questions about indicators? Any questions? Okay. Expectation and independence. We already have seen that if two events A and B are independent, then probability A intersection B is probability A times probability B. So two random variables x and y are said to be independent random variables if any event that depends on only on x is independent of any event that depends only on y. So suppose you consider two events that x is bigger than 10 and y is less than -15. Okay, so that sort of events. So kind of events which depends only on x or only on y. So if these, so now as soon as you have events, you can talk about the independence of events. So if every pair of events which depend only on x and only on y are independent, then you can say that the random variables x and y are independent. Okay, so that's just a sort of a technical way of putting it. So, for example, in 4 independent rolls of a fair die, so you take a fair die, roll it 4 times independently. The random variable, which is the sum of the outcomes of the first 2 dice, is independent of the random variable that is the sum of the outcomes of the remaining 2 dice. Okay. So, the sum of so if you take a die and you roll it 4 times independently, then of course what happens in the first 2 rolls is independent of what happens in the third and the fourth roll. So, the sum of the outcomes of the first 2 rolls is independent of the sum of the outcomes of the third and the fourth roll. This is all that it's saying. So, here is a bit about expectation and independence. So, if x and y are independent random variables, then probability of the joint occurrence of the event that x equal to a and y equal to b. So, if you want to have both x equal to a and y equal to b, the probability of that is equal to the product of the probabilities of individually x being equal to a and y being equal to b. If x and y are independent random variables, then expectation xy is expectation x times expectation y. Okay? So this is the relationship between probabilities and independence. So if 2 random variables are independent, then the probabilities split as a product, and this is the relationship between expectation and independence. So if 2 random variables are independent, then the expectation of their product is the product of their expectations. So this was all about probability theory. So let us now move on to game theory. So game theory is the study of okay, so before we make the switch to game theory, so maybe it's time to take a short 5-minute break, so that you digest all the probability, and after we are back after 5 minutes, we will be beginning with game theory. So, game theory is a study of mathematical models of strategic interaction between rational decision makers. Originally, it addressed zero-sum games in which one person's gains result in losses for the other participants. Today, game theory applies to a wide range of behavioral relations and is now an umbrella term for the science of logical decision making in humans, animals, and computers. So, the typical setup in game theory is that we have a set of P of players assumed to be completely rational. Each player has a set of possible strategies, and for a given game, each player selects one of her strategies without consultation with each other. And so you have a bunch of players, each one has selected a strategy out of his or her possible choices. So this you are dealing with a combination of strategies by various players. So this is known as a strategy profile, and for each collection of strategies chosen, that is for each strategy profile, we have a known payoff for each player. So we know that if player A plays strategy 1, player 2 plays player B plays strategy 2, player C plays strategy 3, then for this combination of strategies, we know that which player will gain what. And the question is to find the optimal strategy for each player. So the game can be represented by the payoff matrix. So each entry of the payoff matrix records a payoff for the players 1 and 2 in all the possible 4 outcomes. So here for player 1 there are 2 strategies H and T, for player 2 there are 2 strategies H and T, and you have combination. So each entry of this matrix is the gain for the player 1 and the gain for the player 2. So notice that this is a zero-sum game, so what the player 1 gains is the negative of what the player 2 gets, right? So gain of 1 is the loss of the other. For example, the top left-hand entry records a payoff of the outcome head-head. Player 1 gets $1 and player 2 loses $1. In game theory, one of the most important concepts is the Nash equilibrium. So suppose you have n players and each player employing a strategy, so you have an n tuple of strategies. So you have a collection of one strategy for each player, so an array of n strategies in total. And it is said to be in Nash equilibrium if one player is departing from it while the others remain faithful to it, results in the punishment for the straying player. So if everyone, a collection of strategies or a strategy profile is said to be a Nash equilibrium if the following happens. Suppose we are all playing a game and you stick to your strategies, respective strategies which give the Nash equilibrium, while I venture to deviate from the original strategy. So then I stand to lose. Okay? So this is the concept of Nash equilibrium, and this must be true for every player. If all the others stick to their original strategies, whereas the player in question tries to move away from the original strategy, then he must lose something. He must be punished. So if that condition is satisfied, then that strategy profile or combination of strategies is called a Nash equilibrium. In other words, it's a state of the game in which no one has the incentive to change her strategy. Saddle point. In the simplified payoff matrix of a zero-sum game, an entry is called a saddle point if it is simultaneously a minimum in its row, a maximum and a maximum in its column. So a saddle point is something. So suppose you have a simplified payoff matrix of a game. So for example, here you could get the simplified payoff matrix, which will be given by the following. So this is 1, -1, -1, 1. So you just record if it is a zero-sum game, you can just record the gain of the player 1, and from that you can immediately deduce the gain of the player 2 because it's a zero-sum game. So this is the simplified payoff matrix for a zero-sum game. A saddle point is a combination of strategies which is simultaneously a minimum in its row and a maximum in its column. Okay? So this is of course not an example, but just to show you diagrammatically what it means. You take the simplified payoff matrix and then take the minimum of an entry of the simplified payoff matrix is a saddle point if it is the minimum in its row and the maximum in its column. So this was so far we were discussing combinations of strategies. So this is called so these are called PO strategies. So each player selects one strategy. What is also of interest are mixed strategies. So in mixed strategies, a player chooses a strategy at random, say with certain probabilities. Then the other player has no way of predicting which strategy will be used. Okay, so that's the utility of mixed strategies. Then the problem now reduces to how do you optimally sort of choose the probabilities with which you will pick the different strategies at any turn of the game. So this will help solve zero-sum games without saddle points and variable-sum games without dominance. So mixed strategies. In mixed strategies, one adopts a probabilistic approach, as we already discussed, by using strategy J with probability Pj, and the Pi's must all sum up to 1 because it's a probability distribution. This is called mixed strategies. So this is going back to the tennis example of from the lecture. So I'm not going over the details of that example here, just to show that the way you deal with mixed strategies is as follows. So suppose so if you are looking at the point of view from one player, then suppose this player mixes the two possible strategies in proportion p. So one of the strategies is probability p, the other strategy is probability 1 minus p. Then what will be the expected payoff for this player? The expected payoff will be dependent on what strategy the other player decides to employ. So what you have to do is that you have to calculate the expected payoff for each of the possible strategies of the other player. So this expected payoff will depend on p, and usually its graph will be a straight line. Okay, so these are the two possible straight lines or graphs for the expected payoff depending on p, where the two different curves or two different straight lines are obtained because the other player might choose two different possible strategies, and there is one straight line or one curve for each strategy. Okay, and then you just look at the intersection of these two straight lines and solve for the value of p at that intersection. At this point, the expected payoff is 2.5 regardless of whatever the other player does. Similarly, for the other player, from the point of view of the other player, you do the same thing. Suppose he mixes his strategies with probability q and 1 minus q. So for each strategy by the first player, you now look at the expected payoff of the second player. So these will again be two straight lines in q, and then these two straight lines will intersect at a certain point. So you solve for the intersection point in q, and at this point the expected payoff for the current player is again the same irrespective of what the opponent does. So what you do is now is that you take the combination of p q, which is solved in this manner by intersecting the straight lines, and this intersection is called the Nash equilibrium in mixed strategies. So each player is indifferent to what the other player is doing, and at this point the game is fair because the expected payoff is 2.5 for both players. Is there any incentive for either player to deviate from the strategy profile? No incentive to change. Indeed, if one of the players changes his strategy, then the other player can exploit this. So this combination is called a Nash equilibrium in mixed strategies. So what is a graph? Mathematically, so this was all about game theory. So any questions about game theory? Okay, so after game theory, let us now move to graph theory. So mathematically, a graph is a collection of points and lines connecting some of the pairs of points. So note that all pairs of points are not connected. So some pairs of points are connected. The points are called vertices, and the lines joining any two vertices are called edges. So in a simple graph, you have if you can have complicated graphs where you can have loops and multiple edges, but if you don't have these objects, then a graph without loops and multiple edges is called a simple graph. So a walk and a path. A walk is a sequence of vertices and edges in a graph such that the sequence alternates between vertices and edges. So it's exactly a sequence of vertices and edges like this, starting and ending with vertices, and each edge in the sequence joins the vertex that occurs immediately before and after it in the sequence. So exactly you proceed in the walk like this. And the walk that starts and ends at different vertices is called an open walk, like this one. A walk that starts and ends at the same vertex is called a closed walk. So for example, this one. Okay. A walk that contains no repeated vertices and edges is called a path. So for example, this one is a path. What is a cycle? A cycle is a graph in a closed walk. A cycle in a graph is a closed walk in which the only repetition is the first and the last vertex. So a cycle is intuitively exactly what you think it is. It is exactly a structure like this. Okay. So it's exactly a cycle with vertices connected by edges. The length of a walk is defined as the number of edges in the walk, including repetitions. So for example, if you look at this graph, then there are 3 cycles of length 4. Cycles of length 4 are called 4 cycles. So this is a 4 cycle. So this is A, B, D, E, A. A, B, C, E, A is also a 4 cycle. So A, B, C, E, A. This is also a 4 cycle. And B, C, E, D, B. So B, C, E, D, B is also another 4 cycle. Notice that here the edges seem to intersect, but that's all right. Okay. Any questions? Okay. This brings us to the concept of degree. So the degree of a vertex in a graph is the number of edges that occur at that vertex, and every loop is counted as 2. So if you look at just simple graphs, then the degree of a vertex in a graph is the number of edges that occur at that vertex. So let dV denote the degree of a vertex V. So for example, if you look at this graph, then you can just calculate the degrees of the different vertices. The degree theorem tells you that in any graph, the sum of all the degrees is equal to twice the number of edges. So in other words, if you take any graph, then if you look at every vertex, consider its degree and sum up all the degrees over the different vertices, then the sum of the degrees is equal to twice the number of edges. And in particular, a consequence of this is that the sum of all the degrees must be even, because it's twice the number of edges, so twice an integer, so definitely it must be even, right? So another corollary of this is the fact that the number of vertices of odd degree is even. So there is a simple argument which explains why this is true. So in the review, we will of course not go into the details of that argument, but in the lecture we covered it in detail. Okay. Any questions? Okay. So let's now go to Euler walks. An Euler walk in a graph is a walk that uses every edge in the graph exactly once. So a closed Euler walk, also called a Euler circuit, is a Euler walk that starts and ends at the same vertex. So it's exactly a walk traversing the different vertices and edges of the graph. An Euler circuit will start and end at the same vertex, with the additional condition that it must use every edge in the graph exactly once. So that's an Euler circuit. And if it doesn't start and end in the same vertex, but it still uses all the edges, it's called an open Euler walk. So, what are conditions? So, Euler circuit does not always exist. So, what are conditions, what are the conditions for an Euler circuit to exist? For an Euler circuit to exist, and it is a theorem that was actually proved by Euler, for an Euler circuit to exist, of course, we are talking about connected graphs. So, from any vertex you should be able to go to any other vertex following the edges, otherwise there is no point in discussing these concepts, because you will never be able to traverse all the edges, right, in a walk. So, we are talking about connected graphs. It has a Euler circuit if and only if the degree of every vertex is even. So, it is a very simple condition. If you look at the graph and you find that the degree of every vertex is even, then the graph will have an Euler circuit. And what is the condition for Euler walk? The condition for Euler walk, that is starting at vertex A and ending at vertex B. So, starting and ending at different vertices. So, this condition is slightly more complicated because it is an open walk, because the starting and ending at A and B are different. So, the condition is that A and B will have odd degrees. So, the starting and the ending vertices will have odd degrees, and every other vertex will have even degrees. So, it's in some sense it is quite similar to the condition for the existence of Euler circuit. Euler circuit exists if every vertex has even degree. For open Euler walk, the starting and the ending vertices have to have odd degrees, every other vertex has even degree. Okay. Directed graphs. So, we regard a graph as a network of roads, and if you look at it as a network of roads, then in cities it is not unusual to encounter one-way streets. In other words, we may include an arrow on each edge to indicate the possible direction of travel. Such a graph with directions indicated on each edge is called a directed graph or digraphs. We can define a walk in a directed graph naturally by allowing the walks that follow the indicated directions. So, it is essentially as if you are walking on the streets of a city obeying the one-way signs. Okay. So, that is a walk on a directed graph. And you can also ask for existence of an Euler circuit or a closed Euler walk on a directed graph. So, what is the condition for the existence of an Euler circuit in a connected directed graph? So, it's walking on the edges of this directed graph, following the directions of the edges, so that you start and end at the same point and you use each edge exactly once. So, the condition for the existence of this kind of Euler circuit is if and only if for every vertex the number of arrows pointing in to the vertex is equal to the number of arrows pointing out. So, for every vertex the number of arrows pointing into the vertex should be equal to the number of arrows pointing out. Okay. So, this is the condition for Euler circuit. So, any questions? Okay. So, let us now move on to the Chinese postman problem. So, given a connected weighted graph or a directed graph G, the problem is to find the shortest circuit that uses each edge at least once. So, a circuit, let us remind ourselves, is a closed walk. So, you start at end at the same vertex, and your weight has to be the least. So, for each edge there is a weight. So, if you take a walk starting and ending at the same vertex, you can sum up the weights of the edges you have traversed on your walk, and this gives you the weight of the walk, and you want the walk with the smallest weight starting and ending at the same point that uses every edge at least once. So, it is exactly the intuition of the postman. So, he has to visit every street in the neighborhood at least once, because he wants to deposit the letters, and the weight you can think of as the distance he has to cover. So, he wants to go out of the post office and cover all the streets in the neighborhood at least once and come back traveling the minimum amount of distance. So, the Chinese postman problem, the simplest case occurs when every vertex in the graph has even degree, for in this case an Euler circuit solves the problem. An Euler circuit will have any Euler circuit will have the minimum total weight, since no edges will be retraced in an Euler circuit. So if there is an Euler circuit, then that's the easiest, because it's a circuit with every edge being covered exactly once. So definitely you cannot go lower in weight than that, because in any other circuit maybe you will cover some edges more than once, so the weight will always be higher. But in general, for instance, in the example that we saw in the lecture, the vertices, there are vertices with odd degrees, and if we know that if there are vertices with odd degrees, then an Euler circuit might not exist. So the postman needs to repeat certain streets. So the problem, the Chinese postman problem, is to deal with the situation, is to come up with an algorithm for the situation when there are vertices with odd degrees. So what you do is as follows: you use the following algorithm. So first you list all the odd vertices, then you list all possible pairings of odd vertices, and for each pairing of odd vertices you find paths that connect these pair of odd vertices which with minimum weight, and then you can sum up these minimum weight paths over all the paired odd vertices, and you go for the pairing of the odd vertices for which the sum total of these minimum weight paths is the least. So in some sense it is adding these paths to, it is kind of, so these are the paths that you are going to repeat, and you are going to minimize your weight, total weight, by going for the minimum weight path for every pair of odd vertices. Now on the original graph, what you do is that you duplicate the edges which have been found in these minimum weight paths, and the length of an optimal Chinese postman route is the sum of all the edges plus the total weight that has been found in the previous step. So the extra weight of these minimal weight paths plus the sum total of all the weights of the edges. And if you take a route, so now if you imagine that these extra minimum weight paths have been put on, now you can imagine that the degree of every vertex is even, and then you can get an Euler circuit for this new augmented graph, because every vertex has an even degree. So you just use an Euler circuit for this graph. Okay. Any questions? Okay, so this is where we stop today, and next day we begin with vertex coloring.